This is me, Naresh, working as assistant professor in IEC department. Today's topic is MOSFET construction and its characteristics in enhancement mode. So before going to this MOSFET construction, first we'll discuss what is the FET. The FET is known as field effect transistor. Why it is called as the field effect transistor means the applied electric field, it controls the flow of current in a given material. So hence it is called as the field effect transistor. So based on the applied electric field, the drain current is controlled by an amount of given your gate to source voltage as well as the drain to source voltage. Hence, this given transistor is called as the field effect transistor. Generally, we know that so we have the two types of the transistors. One is called as the bipolar junction transistor. Another one is the field effect transistor. In a bipolar junction transistor, we observe that the current or a conduction depends upon both the charge carriers, that is majority charge carriers as well as the minority charge carriers. But coming to this field effect transistor, the conduction depends upon only the majority charge carriers, either the electrons or it depends upon the holes. Means based on the type of material we use to construct this field effect transistor. So based on that material, either it depends upon the majority charge carriers, that is electrons or holes. So based on this, so it depends upon only the majority charge carriers. Hence, the FET is also called as the unipolar device. But BJT, so the name itself, it is called as the bipolar, the transistor BJT. Why it is bipolar junction means it depends upon both the charge carriers, that is majority as well as the minority charge carriers. But if you observe the principle of this field effect transistor, it depends upon only the majority charge carriers. Hence, the FET is called as the unipolar device. So based on that, we know that the FET is classified as two types. One is junction field effect transistor. Another one is metal oxide semiconductor field effect transistor. It is also called as insulated gate field effect transistor. So then today we are going to discuss this metal oxide, or it is also called as MOSFET construction. So means where the M indicates the metal, O indicates oxide, S indicates the semiconductor, and we know that FET means field effect transistor. So in this again, the MOSFET is again classified as two types. One is enhancement MOSFET, another one is the depletion type MOSFET. So we have the two types of the MOSFETs. So one is enhancement MOSFET, another one is depletion. So now we are going to discuss the construction of this MOSFET in a enhancement mode, as well as the characteristics, means how it is behaves. So that behavior in terms of the characteristics we are going to observe through by using the methodology is enhancement construction. Now coming to this, the enhancement mode. So if you observe the representation, so we represent it like this, MOSFET. So then, so where M indicates metal and the O indicates oxide, S indicates semiconductor. So again, we have this enhancement mode. We have the two types of the enhancement. So in this enhancement, we have either one is N channel or a P channel. So that is nothing but a N type enhancement mode or a P type enhancement mode. So if you want to create this N type, then we take the substrate is P type substrate. We need to take P type substrate to construct the N-type enhancement MOSFET. If you want to construct a P-type enhancement MOSFET mode, we need to take N-type substrate. So here I'm going to construct the N-type enhancement mode MOSFET construction. So for this case, I'm going to take the substrate is called as a P-type substrate, and this is called as a P-type substrate. And if you want to construct the N-type enhancement MOSFET, suppose if you want to construct the P-type MOSFET, a P-type enhancement MOSFET, we need to take a N-type substrate. So these are the points to remember while constructing the either a N-channel enhancement MOSFET or a P-channel enhancement MOSFET. So if you want to construct the N-channel enhancement MOSFET, we need to use a P-type substrate. If you want to construct a P-type enhancement MOSFET mode, we need to use N-type substrate. Let us coming to the constructing of N-channel or N-type enhancement mode MOSFET. And one more thing, we just now we discussed that we have the two types of the MOSFETs. One is enhancement, another one is depletion. The basic difference between this enhancement and the depletion is only the difference is the channel. In an enhancement mode, there is no channel, internal channel, while constructing the MOSFET configuration. If you taken the depletion type of MOSFET, the channel itself is created while constructing the MOSFET construction. But in an enhancement mode, then we need to induce the channel to allow the conduction across the MOSFET. So that we will discuss later. But do you remember the basic difference between the enhancement mode and the depletion mode? In an enhancement mode, while constructing, there is no channel is established between the drain and the source. But while constructing the depletion mode MOSFET, we need to establish a channel between the drain and the source. So generally, we know that any FET, either JFET or a MOSFET, majorly it contains the three terminals. That is, one is gate, another one is represented as drain, another one is represented as source. So in this MOSFET also, either enhancement or a depletion, we have the three types of the terminals. One is a drain and gate as well as the source. So to construct this MOSFET, we need to come from the bottom to top. So based on this name, the name it is called as a MOS. Then we need to come out from the bottom to top approach. The bottom is represented with a semiconductor. So hence we take another one semiconductor. This is the substrate. That is either P-type substrate or a N-type substrate based on the type of the enhancement mode. So if it is a P-type substrate is for N-channel enhancement mode. If it is the P-channel enhancement mode, we need to choose the N. Then after that, we need to diffuse for this substrate. We need to diffuse a opposite material. That is, generally we know that the two types of the materials, either P-type material or a N-type. So this is the P-type substrate means we need to diffuse a heavily doped N-type material. We need to diffuse on the top of this substrate at the two ends, and one end it is connected to one electrode. That electrode is represented as a source, and one electrode is represented as drain. So hence this is drain and source. Then so means this is O. Then next one we need to O indicates means oxide. So this oxide is here, it is acts as a insulator. The oxide here it is acts as a insulator. So hence we are going to place a silicon dioxide. We are going to place a silicon dioxide SiO2. So it is acts as a insulator media between the two conducting plates. So hence this metal, so this part is acts as oxide that should be filled with silicon dioxide, and here the silicon dioxide is acts as a insulating medium. So hence the next one it contains another representation is metal. So hence we are going to diffuse a conducting part, that conducting material. That conducting material is represented as a metal. So this is a metal, and for this metal we are connecting the one electrode. That electrode is represented as gate. That electrode is represented as gate. Now if you observe from this top to bottom approach, and this is metal, and the second layer is oxide, third layer is a semiconductor or a substrate. Hence this type of the construction is called as a mass construction. So metal, oxide, semiconductor, and this type of the construction is that belongs to field effect transistor, hence it is called as MOSFET. Metal oxide semiconductor field effect transistor. And you remember one point, while constructing this enhancement MOSFET, and there is no channel between source and the drain, or a drain and a source here. Are you clear? So while constructing means, so we can also take, otherwise suppose we can also represent this is source. If suppose if you are representing that this is a source, and then it is a represent up another end, it should be represented as a drain. This is your choice, you can represent anyway, no problem. So one end should be one diffusing, n plus diffusing is represented as the source. Another n plus heavily doped n diffusing material is acts as a drain. So between the source and the drain, and there is no channel, hence, and this type of the construction is belongs to enhancement mode MOSFET. And here the substrate is defined with a p type, and this type of the construction is belongs to n type enhancement mode MOSFET. Suppose I'm coming to, if you want to construct this p type enhancement MOSFET, we consider as the semiconductor or a substrate we taken as n type substrate. On the top we need to diffuse a heavily doped opposite material, and that is represented as p plus. So where the plus indication is heavily doped compared with a normal p type material or a normal n type material. So here also we consider that a heavily doped n type material. So generally we know that this is n type material, and this is I represented n plus means, so this is a doping material is a doping concentration is a very high compared with this n type material. So similarly here also we diffused a heavily doped p type material at the two ends. So one n is represented as, this is connected to one electrode, that is represented as source, and one end, another end that is connected to one electrode, that electrode is represented as drain. Then we need to place a oxide, hence a silicon dioxide is inserted, and that is nothing but it acts as an insulating medium. At the top of this insulating media, then we need to diffuse a conducting material, that is a metal, and this metal is connected to one electrode, that electrode is represented as gate. So here also there is no channel between the source and the drain, but based on the substrate and based on the source and the drain terminal, we can call it this is the p type enhancement mode MOSFET. So these are the construction, how we constructed the MOSFET. So either, so in that in a enhancement mode, and we'll tell you after. So why it is called as the enhanced mode, why it is called as the enhancement mode MOSFET. And just you remember, but in a if you want to construct the depletion, the depletion mode is also looks like same construction, but the only the thing is the basic difference is in a depletion MOSFET, it contains the channel, but in enhancement mode, there is no channel between the source and drain. Now, if you want to identify the behavior, so now we required some amount of the force or a biasing is required to identify the characteristics or the behavior of this MOSFET in a enhancement. So generally, based on the terminals, we know that the source is always it gives the charge carriers to allow the conduction in a given device, that is a field effect transistor. And here the source is, if you let us consider the N-type enhancement MOSFET transistor, the source is made with the N-type material. Means we know that for N-type material, the majority charge carriers are electrons. And for this N-type, the majority charge carriers are electrons, and we know that electron is the negative charge particle. So if we want to diffuse this negative charge particle, we need to apply a negative energy. Means we need to apply the same force. So hence, whenever you apply the negative force on this source, then it diffuse the number of charge carriers from the source terminal to the drain terminal. Then if you want to reach these charge carriers from the source to drain, we need to create or we need to induce the channel between the source and drain. So how we are going to induce this channel, and base for that case again we require some amount of energy between the gate and the source. So hence, so if you want to diffuse the charge carriers or to repel the charge carriers from the source to drain, the source is biased with let us take the source is a biased with a negative charge particle with respect to the drain terminal. So hence drain is a biased with positive. And this type of the biasing is represented as VDD. So why this biasing is required means, so due to this biasing, so it diffuses the number of charge carriers from the source terminal to the drain terminal. But we need to establish or we need to induce a channel to reach all the charge carriers from the source to drain. But here, while constructing this enhancement MOSFET, there is no channel between the, means there is no path to reach the charge carriers from the source terminal to the drain terminal. So hence, we need to induce to allow the conduction for this enhancement MOSFET. We need to first induce the channel between the source and the drain. So how we are going to induce the channel? So which channel is required? Which type of channel is required? So here we need to induce the N-type channel. So that is the reason. And let us observe if this construction, we have the two conducting materials. So this is the metal is a one conducting material, and this semiconductor or a substrate is also a conducting. Why? Because of the substrate is made up with a semiconductor, and the metal is also a conducting material. So hence the substrate as well as the metal, these two are conducting plates. In between these two conducting plates, we inserted the one dielectric media that is nothing but a insulator. Is represented as silicon dioxide, SiO2, where the SiO2 is acts as a insulating media. So that is the reason. If you recall the capacitor principle, so we know that the capacitor contains two conducting plates. So this is the one electrode, positive electrode, and if it is a negative electrode, and these are the two conducting plates. So in between these two conducting plates, a dielectric media is there, that is insulated. So hence here also we are going to apply a capacitor principle to induce a channel or to establish a channel between the source and the drain. Now, if you want to reach the charge carriers from the source to drain, and which type of charge particulars we need to create to reach the your charge carrier or charge particular from the source to drain. And here, based on our construction in the enhancement in N-type enhancement MOSFET, the majority charge carriers are electrons. So hence, to repel the charge carrier from the one place to another place, we need to apply a negative particle. So hence, due to this capacitor principle, if you apply the positive electrode here, then this at this side, bottom next side, it becomes negative. Then another, this is a plate. Now this polarity becomes a positive. Again, at the end of this pole means it becomes the negative. So hence, to establish the negative energy to repel the charge carriers or electrons or majority charge carriers of the source from the source to drain, so we need to establish a negative potential energy. So to establish negative energy, here the gate should be biased with a positive with respect to the source. So whenever, so if you apply the positive energy here, at the opposite plate it ends the negative. Again this here generates the positive electrode, then it generates the negative electrode. So hence, due to this negative energy, a channel is established or a channel is induced between the source and drain. So hence, the detailed diagram I shown here. So what we discussed till now, how it is constructed and which type of energies are required to induce the channel between the source and the drain for a N-channel enhancement MOSFET. So this is the P-type substrate we taken, and we are diffusing the heavily doped materials. One deep material is connected with the electrode is the source. This is S means source, D means drain, and this is the metal. One heavily conducting material, that is a gate. It is connected to gate. And when you apply some amount of a biasing energy between the gate and the source, due to this a positive applied energy between the gate and the source, a negative potential is established between the source and the drain, and that negative potential here it is called as the induced channel, or a channel is established between the source and the drain. So this is the complete information about how we constructed the enhancement mode MOSFET, then how the channel is established to reach the charge carriers from the source to drain or to allow the conduction in a given MOSFET. So these are the symbolic representations of enhancement MOSFET. So then this is also shows a symbolic representation is also shows the each and every terminal is not connected individually, means there is no interconnection between the one terminal to the another terminal. Why? Because of that, in a construction itself, there is no a channel between the source and the drain. Hence, these two are not interconnected. Source and the drain is not interconnected. These are individual, but we need to induce the channel to allow the conduction across the enhancement MOSFET. So one, this is represented the drain, another term is connected to source, and this is silicon dioxide or a insulating media, and this is the metal. The metal is connected to gate. So this is the current flow direction. It shows that this is the for N channel, and this is the P type, the current flowing towards the outside, and so this is called like the substrate. So then again this is silicon dioxide gap. This gap is nothing but filled with a silicon dioxide. It acts as one insulating media between the one conducting plate to the another conducting plate. So this is metal. Metal is connected to gate. So these are the symbolic representations of enhancement mode MOSFET, either in a N type or a P type. So then there are some points what we discussed to allow the conduction across the source, and we use some capacitor principle. to induce the channel between the two substrates or two semiconducting materials. One is the metal and one other is the semiconductor material. Now coming to now we need to identify the behavior of the MOSFET, enhancement MOSFET. So we need to identify the functionality of the enhancement MOSFET type here. To identify this behavior, we have the two types of the characteristics. One is represented as either drain characteristics, or it is also called as the output characteristics. Another one, it is represented as transfer characteristics. So if you want to plot the output characteristics or a drain characteristic, we have the three terms. So we apply the biasing voltage between the drain and the source. Another biasing voltage is applied between the gate and the source. Means if you observe this, construction part, we have the two biasing sources. One is the VDD, one is the VGG. This biasing energy is between drain and the source, and the VGG is a biasing between gate and the source. Hence, due to that representation, so here, if you identify this one, so means VDD means when your VDD is applied between drain and the source, VGG is applied between gate and the source, where D indicates the drain, S indicates the source, and G indicates the gate. Hence, and when you apply this biasing voltage between the drain and source, we need to identify how much potential difference is absorbed between the drain and the source, that is represented as VDS. And similarly, when we apply the biasing voltage between the gate and the source, and we need to observe how much potential difference is absorbed between the gate and the source, it is represented as VGS. With respect to these two parameters, we need to determine how much drain current is flows in this enhancement MOSFET that should be observed as a VID. So hence, the drain current is a functioning with respect to the VDS and VGS, where VDS means the potential difference between drain and the source, and the VGS means the potential difference between gate and the source. To determine this or to identify the characteristics of output of this enhancement MOSFET, so now, so we need to maintain a VGS is a constant. We need to maintain VGS is a constant. Means we need to apply some. At this voltage, we need to plot the characteristics between the VDS versus drain current. Means the drain to source voltage versus the drain current by maintaining the VGS is constant. So this type of characteristics means if you want to find out the output characteristics or drain characteristics, we need to plot the characteristics between VDS and ID by maintaining the gate to source voltage is constant. Suppose if you want to find out this transfer characteristics, the transfer characteristics are plot between gate to source voltage versus drain current by making the drain to source voltage is constant. So by maintaining the drain to source voltage by constant voltage, we need to observe the drain current, how the drain current is varied with a variation of gate to source voltage by making drain to source voltage is constant. So this type of the characteristics belongs to transfer characteristics. And from these two characteristics, you can identify the drain current is a functioning. So here the drain current is a functioning of VGS. In output characteristics or drain characteristics, the drain current is a functioning with respect to the VDS. Hence, I represent it as the drain current is a functioning with respect to the drain to source voltage as well as the gate to source voltage. And from this, we can say that so the FET is means why. So it is why it is called as a field effect transistor means the drain current is depends upon applied electric field between drain and the source as well as the gate and the source. Hence, The FET is also called as the voltage controlled device. So the drain current is controlled by an amount of applied electric field between drain to source as well as the gate to source voltage. Now we'll see in detail how we need to plot the drain characteristics and how we need to plot the transfer characteristics. So let us come into here. So I'm going to first suppose if you want to plot the either drain or a transfer characteristics, I'm going to take the N type enhancement MOSFET. This is the gate, and let us take this is the substrate. So most of the cases substrate should be grounded, and we know this is a drain, and this electrode is connected to source. And now we know that to identify the behavior or the characteristics of this transistor, and we require the two biasing voltages. One biasing voltage is between drain and the source, and based on the type of the MOSFET, drain is a biased with positive pole of the battery with respect to the source, hence the source is biased with the negative. And this biasing energy here it is represented as VDD. Then, and in between, we need to find out the potential difference between drain and a source, that is represented as VDS. Similarly, and another biasing voltage is required between gate and a source to induce the channel or to allow the movement of the charge carriers from the one place to the another place in a proper direction. Then we need to apply a biasing between the gate and the source. Here the gate is biased with a positive pole of the battery with respect to the source, and this is represented as VGG. And due to this biasing, and here we identified a potential difference between gate and a source, that is represented as VGS. Now we need to find out how much drain current is effective or how much drain current is flows by amount of applied electric field between drain and a source as well as the gate and a source. Hence, we need to find out how much drain current is flows, and that is represented as ID. Now we need to plot the drain characteristics in between VDS versus ID by making VGS is constant. So hence, while plotting this output characteristics, the x-axis is represented as VDS and the y-axis is represented as drain current. And now we need to apply some amount of VGS voltage. If you observe the construction part, we know that if you want to construct this enhancement mode, and we taken as this is a p-type substrate, and this is p-type substrate, then we are diffusing the heavily doped to n plus materials. One is called as source, one it is connected to source, one is connected to drain, and this is silicon dioxide, and this is a metal. Now let us consider, and initially let consider the VGS is 0, means we are not connected any biasing voltage between the gate and the source, means there is no force on this gate terminal. What happens if there is no force, means there is no force induced at the opposite plate of the capacitor. Hence, so when the VGS is a 0, there is no channel is induced between the source and the drain. If there is no channel between the source and the drain, hence there is no movement of the charge carriers, means there is no proper movement of a charge carriers, or there is no means there is none of the charge carrier is trying to reach the drain side to allow the conduction across the MOSFET. Hence, at this point, we consider as the drain current is represented as 0. So why? Because of that, we are not creating the path to reach the charge carrier from the source to drain. Hence, and whatever the charge carrier is a repel, that will be attracted with the substrate. Hence, this charge carrier is not reached to the drain. Hence, there is no movement of the conduction, or there is no movement of the charge from the drain to source terminal. Hence, that point here we represented as the drain current is represented as 0. Similarly, so now that is the reason. To allow the drain current, we need to establish the channel between the source and the drain. If you want to establish the channel, then we need to apply some amount of the biasing voltage between the gate and source. There should be always a positive biasing source. Hence, let us assume that if a VGS is greater than 0, but it should be very small voltage. Your VGS should be greater than 0, but it should be very small forward voltage. So let us say if I apply the VGS is some 1 volt. Means here I'm applying the positive voltage, means very small amount of the voltage, means it also generates a small amount of electrodes will be generates at the end of opposite plates. So let us take, this is nothing but your channel. At this point, this is nothing but your channel. Means this is the allowing space to reach the charge carriers from the source to drain. So the area of the channel is very, very less here. So hence the conduction is also a very, very small. Hence the conduction rate is also here very small. If a VGS is increased from this 1 volt, suppose I'm going to increase from 1 volts to suppose 5 volts. What happens here at this point means, so this is, now here we are increasing the force, means the force is increases, means more amount of the force is also generates here. Let us take, this is now my increased force. Now let us observe here. Previously it contains the less amount of the space. Now you have some amount of the space or area to repel the whatever charge carriers are diffused from the source to reach the drain. We created some amount of space to freely movement of charge carriers from the source to drain. And from this representation, so what happens here? So based on this creation of the channel between the source and the drain, so means the number of charge carriers, more number of charge carriers are easily diffusing from the source to drain, hence to allow the maximum current. Hence, the conduction rate is increases here. So if it goes on increasing this VGS, the drain current is also increasing. Why? Because of that, we are creating the more channel to diffuse or to reach the charge carriers from the source to drain. Let us take, if a VGS is a maximum, so means it also creates a maximum space, means a maximum amount of area or a channel is established, or the maximum path is established or induced between the source and the drain. So hence, whatever the charge carriers are diffused or repelled due to this applied drain to source force, the more number of the total amount of charge carriers are diffusing from the source to drain to allow the drain current. So hence, if the VGS is a maximum, the drain current is also becomes the maximum. And from all these three representations, what we observe, if VGS is a 0, the drain current is also 0. If VGS is some small voltage, means that should be greater than 0. And if it is a very small voltage, hence we also observe that the drain current is also very small. Whenever if VGS is maximum, means then we also observe that drain current is also maximum. So from these three observations, so the drain current is with respect to the VGS parameter. Hence, if VGS is increases, drain current is also increases. Hence, this type of the characteristic, this mode, So these are looks like enhancement mode. So it enhances the drain current by enhancing the gate to source voltage as well as the drain to source voltage. Hence, this type of the construction or characteristics or belongs to enhancement mode MOSFET. So based on this observation, so here I shown the some characteristics of drain in a enhancement mode. So here I taken as an x-axis is represented as VDS, y-axis is represented as ID. So we observe that there are some voltages VGS is increased from the 0, and at this point here I consider as VGS is a 0. So what we observe when VGS is a 0, we observe that the drain current is also 0. Hence, this point is represented as drain current is 0. When VGS is some VGS1, I consider some 1 volt. Hence, the drain current is also very small. Means it reaches to some, whenever it reaches to maximum voltage, the current should be saturated. Hence, this point I represented as IDSS1, drain to source saturated current. Then similarly, if a VGS is increased from further volt, let's take I take the VGS2, means I consider 2 volts. ID is also increases linearly, and it reaches the maximum, then becomes saturated. That current is represented as IDSS2. So like that, when I taken the VGS is the maximum, the current is also maximum. At this point, it allows the maximum saturated current, that is represented as IDSS4. So from this, the character, if you observe these characteristics, the graph shows or the parameters are in an enhancement mode. Hence, this type of construction or characteristics belongs to enhancement mode. And from this, we have some parameters. From this characteristics, we have some parameters. Those parameters are called as cutoff region. Another one is a ohmic region. Another one is the saturation region and the pinch off region or pinch off voltage. So we have these are the parameters. So the regions are called as, one is cutoff region, another one is ohmic region, another one is the saturation region, then the last one is this pinch off voltage. So generally we know that the cutoff region means whenever the current is a 0. So at this point, in this case, so in enhancement or drain characteristics, the current is represented as a drain current. And whenever the drain current means we observe that when VGS is a 0, the drain current is represented as 0. At this point, so when VGS is a 0, the drain current is means less than of this part. This entire portion is nothing but this region is called as a cutoff region. And now can observe what is the ohmic region. So we know that ohmic region means it satisfies the linear characteristics, means V is increases, I is also increases. So if you observe this point, up to this point, your goes on means if applied voltage VDS is changes, your current is also changes. And up to this point, then VDS is changes, current is changes. At some VGS voltage, again, the VDS is increases like this, the current is increases like this. So like that, so that is the reason. At which point the drain current becomes, at which point of voltage the drain current becomes saturated or constant. At which voltage or at which point the drain current becomes saturated or it becomes constant, and before that region it satisfies the linear characteristics. Hence, this region is called as the ohmic region. So at this point, what happens if you observe from these characteristics, the drain current becomes saturated. Again, similarly, at this point, the drain current becomes saturated. So similarly, at this point, the drain current becomes saturated. So that is the region. So at which point or at which region the drain current becomes saturated, and before that region is called as the ohmic region. And in that ohmic region, it satisfies the linear characteristics or it satisfies the Ohm's law. Hence, this type of region, so this portion is called as the ohmic region. and at which point the drain current becomes constant or saturated, and that region is called as the saturation region. And that point or voltage, at which voltage your drain current becomes saturated, that voltage is called as the pinch off voltage. So that is the reason. So these are the four important parameters observed from this drain characteristics. One is the cutoff region, one is the ohmic region, one is the saturation region, another one is the pinch of voltage. So the same points I explained here. What is the ohmic region, what is the cutoff region, and what is the saturation region. Now, another characteristics are the transfer characteristics. So what are the transfer characteristics? So means the transfer characteristics are to be plotted between VGS versus drain current by making the drain to source voltage is constant. So from the construction, if you observe this construction, so based on this, again we need to consider the same characteristics. So here we need to maintain this VDD is a constant. Now we need to vary this VGS with respect to this VGG or a VGG. We need to plot how much gate to source voltage is occurs as well as how much drain current is occurs here. So from this, what we observed, if you look at about this transfer drain characteristics, you can observe if a VGS is increases, drain current is VGS is 0. We observe this parameter. VGS is a 0, drain current is a 0. If a VGS is someone means some small voltage, that should be greater than 0. ID is also very small current. And a VGS is a maximum. We observe that the drain current is also maximum. So hence, from this, if you want to plot the characteristics between this gate to source voltage as well as the drain current, if VGS is increased from the 0, drain current is also increased from the 0. Hence, here I am going to plot the transfer characteristics. So the x-axis is represented as VGS and y-axis is represented as drain current. It is also called drain to source saturation current. And this is a given threshold voltage, internally VT. So whenever VGS, your applied voltage is greater than VT, then MOSFET belongs to conducting mode. So it goes on, when VGS is 0, we observe that your drain current is 0. If a VGS goes on increasing from 0, the drain current is also increased from the 0. So hence, the same characteristics we plotted here, and this shows the transfer characteristics. So from this transfer characteristics, we identified that how the drain current is controlled by the amount of varying the gate to source voltage. So we need to observe this point from the transfer characteristics, how the drain current is controlled by the variation of gate to source voltage. So up to this point, today we discussed that the construction of the MOSFET in enhancement mode, and also we discussed that the behavior or the characteristics of enhanced mode under the drain characteristics as well as the transfer characteristics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.